Oualhadj. He's a senior lecturer in the computer science department of Université Paris-Est Créteil Val de Marne. Okay, and he's a member of the specification and verification of systems team in the logic, algorithms, and complexity laboratory. So before his position here, he was a postdoctoral researcher at University of Mons with Véronique Bruyère. And before that, he was also at Marseille. And his PhD was at University of Bordeaux with Hugo Jambert and Anka Mouchol. So I remember he had solved some fundamental problems during his PhD thesis. Now he's going to talk about robust time synthesis. Over to you.
Thank you. Just a disclaimer, I will not be solving any fundamental problems here in this talk, but I will try to give an overview of some recent and not so recent work I did on timed games and precisely on robustness of timed games and what I mean by robustness when it comes to timed games. As every talk about timed games and time systems should start, let me start with the most famous timed automaton in the universe. So I assume that everybody here knows what a timed automaton is. And to be completely honest with you, it is not that important to know how they work for the sake of this talk, but let me just fix some notations and some semantics that we need to use in this talk. So similarly to your usual automata, I have an initial state here, and I have an accepting state here. You can recognize them. You can recognize the accepting state by this double circle and the initial one with the ingoing edge. So likewise, for regular automata, I have a letter, and they work exactly the same with the difference that you have two, you have a certain amount of variables. Here I have two, X and Y, that I will call clocks. And I'll come in a second to how they behave. And also, the unique specification that I'll be interested in this talk is only Bucci objective. That meaning I want to visit accepting state infinitely many times along a given run. So how does a run of a timed automaton looks like? So each configuration of a timed automaton consists of a discrete state that I'll call location and a value for each variable or evaluation of the clocks. So here the automaton starts in the initial state and the value of both clocks will be at 0. And in order to fire this transition, the controller of this automaton has to wait for X to be exactly equal to 1. In this diagram here, it means that he can only fire when it comes to here. Then once he has fired, the clock Y is reset to 0, and the next valuation is over here. And then, same wise, he has to wait, but now in the location L1 until this guard is satisfied, meaning he can fire anywhere in this diagonal, and so on and so forth, and you can create this one over here. So why I'm interested in timed automata in this talk, it's because they will I will play over timed automata, meaning that timed automata will be considered as arenas, and the game I will play is as follows. So I have two entities, a controller and an environment, and in each location, the controller would suggest time delay, meaning the time that he wants to stay in this location, and an action. And the environment will resolve the non-determinism related to this action, meaning he will choose any transition for which the guard is satisfied, and it is labeled by the action given by the controller. And the objective will be to satisfy a Bucci condition. And I will use the same notions, classical notions of strategies for controller and the environment. I'll stick to deterministic strategies, okay? And the goal is to come up with a strategy for the controller such that against any strategy of the environment, the Bucci condition holds. So let us play this game in the previous example and assume that so notice that here I have dropped the letters That is because this automaton is deterministic, and in that case, the game is only one player. The environment does not do anything in the game, and the only goal here for the controller is to come up with a sequence of delays such that the Bucci condition holds. And I assume that he came up with this, the previous sequence of delays, and he has created so far this one. So notice here that when the run reaches this place, then move on to here, he has already completed one cycle, one visit to L1 and one visit to L2, and then another visit to L1, meaning that he has visited L2 once and came back here. And if he wants to enforce the Bucci condition, clearly all he needs to do is to repeat this run, this cycle, infinitely often. So all he needs to do, is to repeat this pattern here. If he repeats this pattern here, he completes another visit to the cycle. So that's what he does here. And now he has to repeat again the same pattern, but from this place, meaning that he has to repeat the same pattern a lot faster than the previous time. But remember that the clocks, they evolve in a dense space, meaning that if I zoom in around this small area, it is actually not that small, and I have as many places as I want. I have as much room as I need, and I can repeat this pattern again and again. And notice that if he wants to repeat this cycle as many times as he wants, all he needs to do is to zoom in as many times as he wants. And then he can just take the advantage of the fact that this continuum of delays exists, and he just needs to play faster and faster and repeats the cycle as many times as he wants. So the takeaway here is that if he wants to ensure infinite amount of visit to the Bucci states, all he needs to do is to zoom in an infinite amount of time. And this is actually considered as this already here. I can convince you that he has a winning strategy. Right? Now, this behavior, if you think really about it, is not completely a realistic behavior. So we do all this synthesis studies and everything for the sake of design of safe controllers. But if I were to say to a designer, okay, here is the specification of your design, of your controller, implement it to me, I don't think that at some point in our lifetime, we will reach a point where the technology will allow to implement such a controller. Why is that? Is that real-life controller that implement this strategy will require infinitely small precision. So I'll call this kind of precision infinite precision, and I'll call this kind of behavior convergent behavior. And this is right there is my motivation for study of robustness. And I'll call a system robust if it does not resort to this kind of behavior. So the goal of this talk is to show you some results related to how we developed a theory that avoids these kind of unrealistic controllers. So the first step to avoid this kind of controllers is to take back some power from the controller. So we want to give some more power to the environment such that he can prevent him from resorting to this kind of, to the convergent kind of behavior to come up with a winning strategy. So I'll play the following game. So in each location, now the controller will suggest a delay and an action. But now, and I'll explain you later, he not only has to play in the guard, but he has to play inside the guard. Why? I want him to play in within a safe distance between the border of the guard, so that he allows the second player, that now we call perturbator, not environment anymore, because I want him to perturb the choice suggested by the controller. I want him to change a little bit the delay chosen by the controller, and then solve the non-determinism. Once he does this, the play proceeds as previously. So let us assume that I want to implement this game semantics over this transition. So the controller wants to play along this transition. And as I said here, he only needs to, if it were not with the perturbation semantics, he could play anywhere inside this guard. But now he has to allow for some perturbation from the perturbator. He only had ensured he chooses a delay. It chooses a delay inside this guard here. I shrunk the guard by a small quantity, and then the perturbator assume that now the environment chooses a delay inside here, and then the perturbator has to perturb this choice by somewhere inside this red area, and then the game proceeds. And then the game proceeds from the blue area. So yeah, here the clockwise is reset to 0, and from somewhere here we set to 0, and the game proceeds. And our goal now is to solve the following game. I'm given a timed automaton and a Bucci condition, and what I ask for is whether there exists a delta such that controller wins the game induced by the timed automaton and this bound delta. So remember, the bound delta is the bound for in which the perturbator can apply his perturbations. So as you most probably know, when it comes to timed automata, whenever somebody asks you to solve something, if you don't know, you should know. Your first reflex should be to check whether it is possible to solve this problem using the abstractions of regions. So before explaining what regions are, the regions that are visited by this set. These are the regions that are visited by this execution, right? And what the regions constitute is somehow a finite discretizations of all the possible configurations that are visited by my timed automaton. Okay? So if you wish for a more formal definition, so here is one. I will not go through it, but all you need to know is that a key idea and one very natural thing to do is that to say, okay, I want to find a Bucci solution of a timed automaton, but I know that I have my regions and they are a faithful abstractions of my timed automaton. So all I need to do is to find a good cycle inside the region, the graph that I obtained by my regions, and then repeat this cycle over and over. Right? And actually, this would work if you were not interested in robustness issues. But now let me convince you in one slide that regions will not be enough to study robustness. So in a nutshell, even though this is a robustness issue, what I need to do is to find a cycle and iterate this cycle. There is no way around this. But robustness happens inside regions. Okay? I can come up with a run that is not robust inside the region that visit the same set of regions, and I come up with another run that is not robust and visits the same set of regions. So assume this is the same region here and here, and this is just the unfolding of some cycle that visits the same region over and over. I have to somehow come up with a way that discriminates between these two behaviors. So here, a set that is pushed towards a border of my region, and this one would not be considered as robust. Why is that? Is that the closer and closer you get to this border, the faster and faster you need to play. And this will create a convergent run, and this will not be a robust behavior. However, this run here is considered to be robust because whenever I start feeling the heat and start feeling that I'm getting too close to a border, I can just escape and escape back to the center of my region. And by just focusing on regions, you can not discriminate between these two kinds of runs, okay? So we need to come up with a different abstraction. And this abstraction exists, and it's based on the notion of orbit graphs that was introduced in 2000 by Puri. Yeah. So this orange line is a hyperplane, and it just models the fact that you are getting pushed and pushed towards the border. And in order to, so the perturbator can, here, this is not robust because these choices here, there are any variation along this orange line will be pushed. It's I can apply the perturbation, and somehow you'll understand later. I can slide an entire hyperplane toward the border.
Okay.
And in order to come up with a robust strategy, you need to find a way to escape not only the border, but you need to escape the entire orange line.
Okay.
Okay?
Thank you.
So here is my notion of orbit graph. And very briefly, what this abstraction does is that it provides a way to store the dynamic in between the variation inside the regions. So not only informs about what regions are you visiting, but it also informs and where, or roughly where in the region you are traveling. Okay, and how it does that? It only remembers what are the corners I visit in each region. So if you consider, for example, the region visited along this cycle, this would be these regions here. And notice that to travel from here to here, if I were in this, corner, to go here, I have only one possible successor, which is to stay in my place. So if I go to this corner, I'm not. If I try to elapse time from here, I'm not anymore in this region. So the only corner that is reachable from this corner is this one. So that is what is modeled by this arrow here. Similarly, if I am here in this corner, and what are the corners that I can reach in this region? So I can either reach the same corner, which is modeled by this arrow, or from here I can elapse time and reach this corner, which would be this one, and this is modeled by this edge over here. Okay? And one extra thing is that once I get a cycle, I can compute what we call a folded orbit graph, which is just the transitive closure of the graph I showed you previously. And this structure stores a very interesting property. That is, I provide two names because it was introduced almost at the same time separately in two work, and they come up with two different names. So just for this reason, to remain true to the vocab, I present these two names. And essentially what you need to understand or to keep in mind is that if my folded orbit graph here is a strongly connected component, then there is a way to repeat this cycle without creating convergence. So I can somehow robustly repeat this cycle whenever the cycle is a strongly connected component. So now already I have the tools to characterize when a robust strategy exists. And how is that? So first, I'll say that so yeah, I'll come up to this in a second. But first, yeah, as I said, when the folded orbit graph is a strongly connected component, you can iterate this folded orbit graph until some point that it creates a complete graph. So the successive iterations of your folded orbit graph will create a complete graph. And what you can prove is that whenever this folded orbit graph is complete, so the reachability relation in between values inside this region is complete. Meaning from any valuation, I can go along this cycle and reach any other given valuation. So now what I need to do in order to find a robust strategy in my regions, all I need to find is a strategy for the controller that only relies on this kind of cycle, that relies on cycle that creates complete folded orbit graphs so that they can ensure the Bucci condition in a robust manner. So this is how the results look like. So you are given a time automaton. You compute its region graph. Because of the time semantics we have, or the gain semantics we had, on the top of this region graph, I can play a game. And this game looks something like this. So the controller chooses the next region, chooses a set of possible regions by proposing an abstract delay. And then this will induce some non-determinism, and the perturbator will just resolve this non-determinism. So over this game, the antagonist player does not have any timing powers. He only solves the non-determinism. And I'll say that the controller wins if he comes up with a strategy such that this strategy satisfies the Bucci condition, and every Bucci cycle is stable under iteration, meaning the folded orbit graph induced by every Bucci cycle is a complete graph. So let me just try to convey a little bit of intuition for this kind of for this result. So assume that this is the unfolding of a strategy of the controller, and this region and this region is the same, and here and here is this is a cycle. So he needs to come up with a strategy such that, so his strategy, what it does is that it aims at repeating these cycles again and again. And because I know that every folded orbit graph along this cycle is complete, I know that I can come up with a way such that from any valuation here, so remember, when the folded orbit graph is complete, the reachability relation between valuation is also complete. So what this means is that along those red cycles, I can come up with a way such that from inside here, before repeating this cycle once, I can escape from the borders and push the game again inside the region and be safe from within the borders. And this is due to the fact that the reachability relation between valuation is complete. Conversely, if this does not exist, then at least one of those two cycles is not a complete, has not a complete folded orbit graph. And for this, we can build a concrete strategy. We can build a strategy for the perturbator such that he can apply at every step of the game, he can apply the same perturbation toward the same direction and pushes the play towards some border and block the perturbator. So the corollary of this, I guess, is that the robust synthesis is X-time complete. And why is it X-time complete? Is that because you need to build, for this, I cannot rely on on-the-fly technique. I need to store the entire region graph in my memory. But notice that at the first sight, you could think of, but you still have to check for this orbit graph notion. But checking for the orbit graph notion and condition, you only need to check for, I can reduce it to another Bucci condition, which is not that expensive with regard to the region graph, and just build a larger Bucci condition and come up with a Bucci game that encodes both conditions, okay? So yeah, so far what I have showed is that if I have a game semantics where the perturbator applies his perturbations again and again in a very clever way, then he can either enforces the he can pushes the player toward a border. But at the beginning of the talk, I told you that I'm interested in applications. And clearly, just assuming that whenever you want to come up with a correct control, there will be an antagonistic entity that will push you toward these borders and choose this one chosen perturbation to kill you is not a entirely realistic notion. So let's say, okay, is the game any easier if now the perturbator only, if the environment only resolves the non-determinism, but the perturbations are chosen at random? So the answer is no. The game is not any easier, and moreover, the same condition over the region graph is sufficient to solve the problem. So I solve exactly the same problem, disregarding, I'd say, the probabilities, and the same technique holds. Moreover, in this case, either the strategy will ensure the Bucci condition almost surely, or the Bucci condition will not hold almost surely. There is no in between. Okay? So we can also come up with a semantic that falls in between. So now I give full power of the environment to some random entity. And I ask, okay, can I come up with a strategy that ensures the Bucci condition against an environment that randomly resolves the non-determinism and randomly perturbates? So in this case, the same complexity holds, but you need to slightly alter the conditions that I came up with earlier. And here notice that you have to solve a game where you combine between a probabilistic condition and a sure condition. So the second one is not probabilistic. And what we are able to show is that if the controller wins this game over the region graph, then he wins the robustness game over the timed automaton. Let me just mention that in this, under this game semantics, winning almost surely does not coincide with winning with value 1. So when I say winning with value 1, I mean, can I win with probability arbitrarily close to 1 under some given epsilon? And when I say almost surely, I mean, is the limit over all the probability or all the of one given strategy ensures me that I win with measure 1. Okay, so these two notions does not coincide under this semantics. And to solve the value 1 condition, I need to alter slightly the winning condition. Okay. So let me recap here what I have showed so far. So I have some timed automaton, and I gave you some game semantics for robustness over this timed automaton. And what I showed is that there is a way to come up with strategies that ensures a Bucci condition and that do not rely on a convergent behavior. So this behavior, that's the behavior that I call not realistic. So some few things that, one very important thing that I have not said is that in the previous game semantics, I did not allow for punctual moves. More specifically, I did not allow for punctual guards. So a punctual guard means a guard that is written as a clock equals to a constant, okay? So in the previous semantics, what I said is that under this kind of guards, you can never come up with a winning strategy. Okay, and I also showed some probabilistic semantics. But I have one minor problem with this semantic is that under the previous semantics, and when I'm not allowing punctual moves, if my game is not deemed robust, I just throw it. I don't have any sort of way to understand from where the non-robustness comes. What is the origin of non-robustness, okay? So this brings me to this notion of repair, and it's a rather extreme notion of repair, but bear with me. Assume that we have this cycle here, and this is the cycle from the previous automaton. And if you remember, this cycle is not robust. So one way of thinking of repairing non-robust automata is to say, okay, this automaton is not robust because I can perturb in this transition, I can perturb in that transition, and then this brings troubles. What if I say, okay, I fix some transition to be exact. I fix these transitions to be exact, and I say, okay, what happens now when the transitions are exact? What happens if the perturbator does not get a word to say over these transitions? So this is at the same time a good and a bad example, because you have to trust me on this. This is the only way to repair this automaton. So the only way to repair this automaton is to make all the transitions precise and not perturb anywhere. So this is how it goes. So our idea of repairing a non-robust automata is to change some transition and say, okay, over these transitions, the perturbator does not get a word over what happens, and see if it still can come up with a robust strategy. So what I need to do is now to solve the control problem, the robust control problem with punctual guards, okay? Because under the previous semantics, the semantics did not allow for punctual guards. So the way it goes is that now in each location, the controller chooses a delay and an edge, not an action, but an edge. And now if the guard related with this edge is punctual, then the game just proceeds. The play proceeds, and there is no perturbation applied. If it is not, then the perturbator applies his perturbation as previously, and then we repeat. So basically, we need to, because there is some Bucci condition somewhere, and we need to repeat cycles, we need to discriminate between good and bad cycles. So the way here we propose, the way we solved this is as follows. I need to find a criterion that discriminates between what are those cycles that I can repeat and still maintain robustness. Previously, when everything was perturbable, what I've said is that if the reachability relation in between along a cycle is complete, then this cycle can be repeated in a robust manner. Here what I say, and you have to trust me on this, is that if the reachability relation along this cycle is an equivalence relation, so a little less than a complete relation, just an equivalence relation, then I can repeat this cycle robustly. But yet I have to come up with a way to find if the reachability relation is a equivalence relation or not, because this is an equivalence relation between the values inside the region. And what we can show is that if the folded orbit graph along some cycle has this structural property, that is a union of a disjoint union of complete subgraphs, then it is an equivalence relation. And under this condition, you can repeat this cycle robustly. So this is an example of a folded orbit graph, which is a disjoint union of complete subgraphs, right? And the immediate consequence is that the controller wins if there exists a Bucci cycle whose folded orbit graph is a disjoint union of complete subgraphs, right? And why is that? Very briefly. So yeah, just one word of vocab. In this kind of setting, I will call each equivalence class a slice, okay? And the vague intuition is that in order for the controller to be able to win, they have to somehow find a way to compensate in between the perturbations, right? So because this slice is an equivalence relation or the reachability relation, it means that within this slice, every variation is reachable from any other. One way you can see it is that here, because this strongly connected component here, you can think of it as this reachability relation described by this strongly connected component can sort of moves the valuation along this cycle, this slice, but can never shift the weights toward this corner. So there is no valuation that can escape from here and reach here. Okay, but this also applies for the perturbator, meaning that he cannot find a way to apply perturbations and push or make the play to go toward one border or the other. He can only somehow try to get closer to this face or to that one, but because the reachability relation is complete along this slice, the controller somehow can always escape and compensate and falls back inside the slice. Okay. Similarly, if it is not an equivalence relation, then you can guess that the perturbator can take advantage of this edge over here and eventually forces the play to escape from this slice and go over to this corner. Okay? So yeah, so he can forces the play to escape from this slice to this new slice, and so on and so forth until the game converges toward the corner. Okay? So this brings me to this recap here. If you want to repair now an automaton, a non-robust timed automaton, all you need to do is to find the transition and change it to a functional God, and then apply the following algorithm. You guess a cycle. So all the steps here are performed on the fly. So you guess your cycle. You check that it is a Bucci cycle. Then again, on the fly, you check that the folded orbit graph induced by this cycle is a reachability relation, an equivalence relation, sorry. And then you answer. So this can be performed in p-space, with a p-space algorithm, and it only works. So far, this is only the repair of deterministic automata. Okay. And this brings me to the end of the talk. So what I have presented here is a game semantic for modeling perturbation. But what I also presented is that there is a way to characterize convergence phenomena, and we come up with an algorithm that synthesizes what we call robust strategies. That is, strategies that are able to ensure the objective without relying on too precise behavior, meaning they do not rely on convergent behaviors. Okay? So to perform this, it was hidden in there, but we use some symbolic data structure, and these are useful to compute parameter. Because when you claim that a system is robust, you need to ensure that it is robust within this parameter. It is robust to any perturbation within this delta, and this parameter is computable. Okay, and I also presented a notion of repair. That this repair of non-robust automata only works for deterministic timed automata. So as a future work, it is natural to try to extend the notion of repair to non-deterministic setting, but also in the broad project of trying to come up with an implementation, come up with symbolic approaches that allow for scalable implementation, and also study this kind of problems in the more general setting of concurrent games. Okay, thank you.
Thanks, Youssouf, for the very nice talk. It also robustly got to you. So, yeah, any questions?
Hi, thanks for the talk. You mentioned that you had some notion of probabilistic perturbations. I had a question regarding that. I mean, what is the distribution that you're taking on the perturbations, and does anything actually depend on the choice of distribution?
So, yeah, so we chose the uniform distribution over the, but it does not matter what distribution you choose. Okay,
It's fine. I mean,
yeah, so we fixed the distribution just for the sake of making the proof work. But any kind of distribution will work. And also that you can guess that, but from the fact that either everything is almost truly robust or nothing is almost truly robust. So it is a asymptotic behavior, and it does not really depend on the exact values of the distribution.
yeah. So in some sense, even if you don't know the underlying distribution, this will sort of still work up.
Yeah, it's
some nice.
Yeah, if there is a chance that it will go wrong, it will definitely go wrong. Yeah.
Yeah.
Yeah, thank you for the talk. I also wanted to ask about the probabilistic perturbations. Could you go back to that slide? I wanted to see it again.
This one?
I think stochastic perturbation. Yeah,
Okay.
this one. I think. Yeah. Yeah. So, could you give an idea of the proof, roughly how this goes? Because I was wondering if some kind of zero-one law was used here.
So yeah,
Like-
it's exactly that. So as you can see here, in order to check for the almost sure winning, we only check for a deterministic condition over the region graph. Okay, and what this hints to is that if your strategy is not robust, it only requires a finite amount of perturbation to happen in the good order, so that it pushes the play toward a corner, right?
Yeah.
And if this might happen, it will almost surely happen because it is only a finite. You only need for a finite prefix to happen inside your game, your play. Okay.
Okay.
And
Okay.
if there is a chance for this to happen, then you can use Boyle controller-like arguments to ensure that it will almost surely happen.
Right. Okay. I think I get the idea. Thank you.
Okay.
Thank you.
Questions? So I have a question. Because for the general case, it is X prime,
Yes.
right? X prime complete and so on. So I'm just wondering if you look at restricted versions like automata with 2 clocks, automata with 1 clock, and so on.
No. No. All I can say is that it retains the same complexity as timed games without robustness. And the
Okay.
complexity really does not come from checking the robustness.
I see.
It
Okay.
only comes from
I see. I see. Okay.
I mean,
Yeah, I
it's
see.
too technical, but checking this folded orbit graph condition, it is in an X time condition because you have a sort of exponential number of possible graphs, folded orbit graphs, right? If you have less clocks, you will have less graphs, right? And then if you have less clocks, it can only reduce the complexity.
Correct. Yeah.
But under the condition that the complexity of the general sort of game reduces also.
I see. Okay. Thanks. Just another one, maybe since we have a couple of minutes. So for that, for the one with punctual guards,
Yes.
so you got p-space
Yeah.
upper bound. Is it because of the determinism?
Yeah. So when it's deterministic, all we need to do, I mean, not all we need to do, but it's somehow not a real synthesis problem, but it's just an emptiness problem. You just need to come up with a,
I see.
yeah.
Oh, okay.
So you don't need to store the entire
I see. Okay.
region graph anymore. So you can combine in between on the fly techniques.
So if I were to look at deterministic without punctual guards,
Yeah, it is also p-space.
space,
Yes.
okay. Thanks. Yeah, of course. Anything else? Good. No, let's thank Youssouf again for the wonderful talk. So the next session starts at 2:55.
So there is a photo session after the next session, so at I think 3:36. So just wait.